Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in the University of Helsinki, and I'm a cosmologist. So that means that I study the universe, the contents of the universe, how it all evolves, how it all interacts. It's a great topic. I love being a cosmologist and I love chatting to everyone about all of the cool things happening in the universe and about all of the cool science I get to work on. It's really fun to be a scientist and it's really fun to chat to people. Hey, Ange, in first, great to see you as always. So as always, if you're not following me on YouTube, please do head over to the YouTube channel, subscribe, leave a comment, click the like button, all of the usual things to boost engagement. It really does help. And I really do appreciate everyone who does that. So today we're going to be talking about an unusual topic that I haven't covered before on the stream, but that is a really, really important topic to discuss anytime we talk about cosmology or science in general. On today's topic, I'm not going to be discussing alone. I have a guest with me today, so I'm going to bring Suksu up on screen. Hi, Suksu. Welcome to Cup of Cosmology.
Thanks for the invitation.
Sure. Do you want to introduce yourself to everyone here?
Yeah, sure. So I'm Suksu Räsänen, a cosmologist, also at the University of Helsinki. I've worked on a number of things, from the cosmology of extra dimensions to the effect of cosmological structure formation on the expansion of the universe and on light propagation, cosmic magnetic fields, and the period called inflation in the early universe, which is our best explanation currently for the seeds of all structure.
Yeah, inflation is a very cool topic. We actually had a guest 2 or 3 weeks ago talking specifically about inflation, also from Helsinki. That was Lorenzo, a PhD student in our group, talked about inflation a lot. But it's a topic that we can definitely always talk more about. Let me just say hello to all of the regulars and all of the new people coming in. Hey, David Dunn, James, Cosmo Blend, first time seeing you here in the comments. Paul, great to see everybody here as always. Really, really nice to see everyone joining. Great to see you all. I know I was off last week, so it's always nice to see that you come back even when I miss a week. So great to see everyone. We already have a comment from Paul that lets us jump straight into the first question we wanted to address. So Paul is saying here, I'm looking forward to hearing this. I'm wondering if it's going to be about beauty in equations, beauty in images, or what we're actually talking about. So let's use that as a jumping start and ask the question of what do we mean when we say beauty in physics? And this is something we can approach from several different perspectives. So I think you had 3 different ways you wanted to define this. So let's start with the first one. What do we mean when we say beauty in physics?
Yeah, so both of the above and more. So there are at least three ways in which we can think about beauty in physics. And the first and the most straightforward is just what some might call the beauty of physical phenomena, but I would call the beauty of the realizations of physical laws. So, for example, if you think of the cosmic microwave background, the right on cue. So this is an image of the sky on microwave frequencies with the rubbish from the Milky Way and some other nearby sources removed. Now, many cosmologists find this image to be very beautiful. And as would I think some people who are non-cosmologists, sometimes I've actually asked the question when I've talked about beauty in physics. I've shown this to a lay audience and then asked, do you find this beautiful? And I've shown different images in physics. It's very interesting to see kind of reactions people have. And of course, people thinking, that the sun is beautiful, that snowflakes are beautiful, or whatever. So this is the simplest way in which we can think about beauty in physics. And even then, so it's purely this visual impression of beauty, but even then, it's colored by what you know and about the image and what you think of that the image is. So, for example, when I look at the cosmic microwave background, I think that, okay, these are, first of all, the impressions left by quantum fluctuation in the early universe. So I'm looking at something that's very early, that's very primordial, that goes back to the first fraction of a second. And on the other hand, these are the seeds of the structure we see today. So this is something that has led to the evolution of planets, galaxies, and so on. And this, of course, affects my aesthetic impression because then I attach extra importance to this image. And I bet that if you show people, the same image, but tell them, this is a bacterium, or, this is rust at the bottom of a boat, or you tell them, this is a star cluster or whatever, then they would react differently when asked, is this beautiful or not? So even there, it's not purely visual; it's also affected by what you know.
I think that's an excellent point, and I'm glad we're using the CMB as an example of this, because I have heard people describe the CMB as like pigeon droppings, which it has a fun historical precedent, because that's actually what people initially thought it was when it was first detected. If you don't know what it is, honestly, it's just orange and blue dots, and yeah, it's not something that you might hang up on the wall without knowing what's behind it. But then you hear the story of this is, the earliest photo we have of the universe. It tells us so much information. And then it takes on special meaning just because of what's behind this image. So I do think there that, again, what you know about the image is going to cloud your perspective. But I love that we're using the CMB as an example, because my regulars know CMB has to appear in every one of my streams, and it took less than 5 minutes today.
Yeah. So Paul has on the chat says that, in a museum, something thousands of years old is beautiful to us. So the CMB at billions of years old takes the prize. But I think this is a good example, because when you're in a museum and you look at an object and there's like a rock, and you're told, okay, this rock is 30,000 years old and it was used by early humans, then you look at it differently when if you're told, okay, we just picked this rock from from the backlot yesterday. So there's that. But there's a second way in which there's beauty and aesthetics related to physics that you already alluded to, which is story. So of course the CMB, is connected with a story about the universe, a story about how we came to be, a story about what is our connection to the early eras of the universe, and what is our relation to the rest of the universe. So but also, if you think of how cosmologists approach cosmology, or in general how physicists approach physics, then the language is that of mathematics, and this is a completely inhuman language. It has no human. You write an equation and it has no human resonance, which is one reason why it's easy to do physics, because you don't bring your preconceptions into the mathematics, or if you do, you'll quickly find out that you're wrong. But then when you look at the results and you write them in words, first of all in research papers, but especially when you talk to non-physicist audiences where you don't use equations, then you necessarily use these, not the language of mathematics, but these social languages like English or Polish or Finnish or whatever, that have evolved, to communicate about our internal states, and to structure our internal states, and to communicate about, in social circumstances. So then when you talk, these words necessarily are laden with social presuppositions and, and ideas. So if you talk about, a star collapsing, or if you talk about a planet being born, or if you talk about, all the light in the universe fading away or something, then this immediately sounds like, there's certain not aesthetic imagery, but also sort of somehow value laden imagery, because you associate these words with human light and human experience.
I think this is a really important point to make here, because stories is, as you were saying, stories is usually how we talk about physics, both to general population and among ourselves. We're always telling each other stories about our results, about our equations. These stories are very much shaped by our own experience, by our own perspectives. And it also adds in the element that a lot of people like to think science is not political, but science is very much based on our own preconceptions and the stories we're going to tell, which will come from our pre-existing knowledge. So I think it's really important to make this point here that, we talk about stars being born, and this is just to relate it to human terms, but that doesn't necessarily mean there's any actual birth. It's just the beginning of a star. And we tell it in these words to make sense both to ourselves and to each other. And I think it's really nice to emphasize that this is going to be a very subjective story that we're always going to tell.
And it's also, there's also something that, because cosmology really studies where we have come from, where humans have come from, where, in a very wide sense, where the world has come from, and also gives us information about where we are going to. And this is, of course, something that for the vast period of human history is something that was done by myths, by mythology. And mythology, of course, has very strong, aesthetic appeal, And I think that, cosmology has some of the appeal of myths, but the difference, of course, that these are not stories that we have made up, to human preconceptions. It's something that we have learned through observation, through mathematics, that this is something that is actually real, and then we tell stories about, we try to frame it in words. But it's like, it's like a mythology with, no gods, no heroes, and no morals also.
Yeah, I think there's a very nice comment by James here in the chat saying, I think the universe is a mystery story, and that's what keeps me coming back for answers, and that's beautiful. And I would agree there. The fact that we can tell these stories, the fact that we can try to answer these unknowns with our maths, with our equations, with our stories, is one of the things that makes physics itself so beautiful, because we can try to find understanding. So I think that's a really nice point there, and it keeps you coming back for more because it's a mystery. Yeah, honestly, that's what keeps me doing it as well. The day we know everything will be a very boring day in physics.
So, and the third aspect, which I think is maybe the most difficult to appreciate, is of beauty in physics, is the beauty of the laws of physics. This, in some sense, is a more pure, I would say, form of beauty. And if we think about it historically, so if we think, for example, about circles, so the simplest idea of how planets move in the sky is that they move on a circle. Then, if you do a bit of observations, the ancient Babylonians already knew that this is not true. Because sometimes planets, they go forward and they go back, and their size on the sky changes and so on. So then you have circles, and then you add epicycles. This was the idea of Ptolemy in around 100, the year 100. And Copernicus then restored the idea of circles, although he did have also epicycles, but the idea to place sun in the center, and then you get a much simpler model where circles are again, restored to their rightful position, that objects move at a constant velocity on circles that move on circles. And Copernicus's idea was governed by beauty. Like, it wasn't governed by observations. The problem, it wasn't that his model that he adopted his model or proposed his model because it fit the observations better than the model by Ptolemy. And of course, then Copernicus' model was then developed by Kepler, who then, who then looked at observations and noted that no, the orbits of planets are actually ellipsoidal. And then if you go to Newtonian theory, which says that no, there's no predetermined one shape. Instead, you have laws of physics, so that together, the interactions between all of the planets and the sun affect the orbits. So then it's actually not pure ellipses either. And so in some sense, you might say, okay, you go from less symmetry, from this, you go from more symmetry to less symmetry. So you go from to, let's say, very exaggerated disturbances in the orbits that you have in Newtonian gravity. But Newton's laws, but in Newtonian theory, so if you think about what determines the orbits of planets, so what are the laws that govern, the solar system, then those laws, you have the gravitational force inversely proportional to the square of the distance and acting, in the direction of the planets, so it just pulls them together. So this law is the same everywhere in space and in all directions in space. So actually, this law has much more symmetry than the realizations of these laws. I mean, originally, even if you have a circle, it's just symmetric, so that you take the central point and then you rotate around this, on the plane. Now, if you take Newton's laws of gravity, you can rotate in 3 dimensions in space and also choose the origin of space as you want, but these laws are the same. So Newton revealed this new, deeper form of beauty that has then, I think, become, one of the biggest discoveries of humanity, that you have beauty in the laws of physics. And I think it's sometimes, I mean, it's related to simplicity, it's related to symmetry. I think I've sometimes said that it's like if you have music and you couldn't hear it, you could only read the notes, then physicists are the people who read the notes and hear the music in their heads. But I think one can put sort of use also a different allegory that also somehow brings out what's the symmetry and simplicity, namely the laws of games, the rules of games. So if you think about chess, so chess is a beautiful game because it has a very simple symmetrical playing board. It has simple rules, and the beauty of the chess setup, so the rules plus the initial board, is something that exists beyond the realization of the beauty of any game. You can think about different chess games, and there are some like historical chess games that are very beautiful. But when we think about the beauty of chess, we don't think only about the beauty of the realization, so the games, but of the rules themselves. And now if you think, for example, how to improve chess, it's very easy to invent new rules for chess. I think almost everybody, at least when I was a kid and I played chess, I invented new rules. What if if you move like this, then this happens and so on. But it really doesn't become more beautiful. So it's quite difficult to, although people do like, make up new rules. New rules have been introduced to chess, but it's difficult to make a rule that makes it more beautiful. So their simplicity is part of the beauty, but it's not only simplicity.
Yeah, I think it's really nice. You covered a few parts there that go into this, what makes a law, an equation beautiful. And you mentioned symmetry and you mentioned simplicity. And I think the story of how planets move is a really good way of doing it, because this idea for us that circles are the most symmetric and therefore the most beautiful is what led to the wrong idea that we were at the center. And just this idea of moving away from the circles to the ellipses based on observations, then actually revealing more symmetry that we hadn't seen. I think it's really interesting how you think we might be moving away from this concept of symmetry and beauty, but then you find more symmetry and more beauty when you actually find the equation that works. There's a comment here by Paul, which I think is really nice, and that is actually where I wanted to take this discussion anyway. So in this sense, is beauty a principle, in the sense that laws of physics must obey this sense of beauty? Or is this something that we try to find and try to impose ourselves? So do you think beauty is a pre-existing condition for the laws of physics?
Yeah. I think it's useful to think, maybe to frame this question by looking at in which way do we see theories of physics as beautiful or ugly. So if you think about Newton, and also to note that theories of physics have their associated languages, mathematical languages, so certain branches of mathematics in terms of which they look simple, because they reflect the underlying structure of these forms of mathematics. So for example, if you think about Newtonian gravity, then there's a thing called vector calculus. And if you write it in terms of vector calculus, it looks nice and simple. And if you didn't know what vectors are, if you didn't know how to rotate space, for example, things would look a lot more complicated in Newtonian gravity. Then if you think about general relativity, then if you write general relativity in the same language, vector calculus used for Newtonian theory, it looks really ugly. It looks really complicated. It's difficult to understand what's going on. It's difficult to see why the structure is like this. But if you express general relativity in the language of differential geometry, which is the natural language for general relativity, then it looks beautiful, and then it's Newtonian gravity that looks like it's really missing something. And to make it work, you have to bend over backwards, and somehow you see that there's no point, to having a theory that's somehow missing parts. In practically speaking, that somehow treats time and space differently, whereas if you look at it from the point of view of different geometry, they're really part of the same thing. So in this sense, I do think that beauty is important, for all branches of physics, but there are different aesthetic standards. There are different notions of beauty in physics. And if I may use a comparison, that if you think about, I should have probably I should have thought of this beforehand. But if you think, for example, classical painting versus cubist painting, then if you take a cubist painting and apply the standards of beauty of classical painting, say classical portrait painting, to it, it looks ugly. But on the other hand, it's also true that if you apply cubist standards of beauty to classical portrait painting, it also looks ugly. So you have these different notions. What's different in physics is that things are not only ugly and beautiful, they're also true or untrue.
I think that's a really nice example there because, as you say, the way we value beauty in one thing or in another very much depends on the frame in which we're considering it. In the same way as before, we were saying that the image of the CMB itself is not necessarily beautiful, but it's the understanding that gives it beauty. I think it's also very important here when discussing theories and equations of what makes them beautiful. Because I've heard people argue, for example, the standard model of particle physics is very beautiful. And it's mathematically, it's not necessarily the most simple or the most elegant expression that you can come up with, especially when you start developing all the terms and it occupies a whole page. But it is what we've seen is necessary, and it is beautiful in the way that it can explain those phenomena that we've seen. But then if you compare that to general relativity, which can be expressed in a very, very short form, it's a very different standard of beauty we would apply. And I would say that both are beautiful, but just in different contexts. So I think it's important to always bear in mind of where we are within, when we're talking about beauty, what we're using as our frame of reference in order to discuss that.
Yeah, that's the thing that, like, when developing new theories of physics, the most difficult thing historically, well, one of the most difficult things, has been to develop the new language and to adapt the new language. So in the case of general relativity, it was really key that Einstein and others who developed it adopted differential geometry that was developed, built by mathematicians, discovered by mathematicians in the previous century, in the 19th century. And it's the same with painting. It's nowadays it's very, just go on a painting course and you will learn how to do cubist paintings. It doesn't require any great insight. And go on a GR course and you will learn the basics of GR. If you have the mathematical background, you can learn it in a few months. But the key is to be first is to discover this new language. Like Stravinsky said, that he discovered a new language for the opera, and it was this. Some people found it barbaric at the time because it was such a break with previous conceptions.
Yeah, I think it is a very important point to make there. We have a very interesting comment from David here, David Howden, that there are evolutionary psychology theories about why different people find different types of art beautiful or different things in nature beautiful. David Howden is wondering if we could use that in a similar way to how different people find different things within physics beautiful, or if there's more of a shared idea that everyone agrees that general relativity is a beautiful theory.
Yeah, important question. So because what's important in physics is to hone your sense of aesthetics based on observations. So based on truth, and and to learn to discard some aesthetic ideas that you had before, and to be led into aesthetic ideas that are tied to truth instead of those that are tied to things that are untrue. So I think people who are familiar with the structure of general relativity, for example, would all say that it's beautiful. So, but on the other hand, if we look at the different, like you mentioned, the standard model of particle physics. So if you look at then different extensions of the standard model of particle physics, of which there are hundreds and hundreds, although most of them are variations on a few ideas like supersymmetry or extra dimensions or technicolor or whatever, then opinion in the community is sharply divided on whether these things are beautiful or not. And it's simply because we don't know whether they are true or untrue. If one of them was found to be true, then I'm sure people would again adapt, and then they would change their view of aesthetics, accordingly, to say, okay, if this is true, then I will change my sense of aesthetics so that this thing actually also looks beautiful.
Yeah, I think that's a really important point. That it goes back also to what we were saying before about when you understand something, it becomes more beautiful. So if we know that something is a true description of reality, or at least the most accurate description we have, would we naturally embrace it as being more beautiful? And then you can also think of things like modified gravity. When people try to modify Einstein's general relativity to explain some phenomena in the universe. And this is taking something that everyone agrees is a beautiful theory and modifying it, which is why some people are immediately like, oh no, what are you doing? But then if it turns out that one of these modifications proves to be correct, will we then all agree that this is actually the new ideal standards of beauty for general relativity? Or would we default back on Einstein's as still being the most beautiful?
Yeah. So, I mean, I think this is a very I consider this a very loaded example because most of these, because these modified theories of gravity are so ugly from the point of view of general relativity that you would have to have, I think you would have to have a new theory that has different notions of aesthetics and that is a bigger structure from which these emerge. Because if you look at them alone, I really find it I really find it difficult to view them as, as aesthetic.
Yeah, I think it comes back to the idea of simplicity, because Einstein's general relativity is essentially very simple. Obviously, it's not, it takes a while to understand it, but it can be expressed in a very simple way. And when we go to these modified gravity theories or models, usually you add expressions in, you add terms into it in order to fit different, perhaps, observations or different predictions or different things you want to do with it. But then we could also go back to Einstein's general relativity and say that there we had to add the cosmological constant in there in order to fit in with the accelerated expansion of the universe. And if you take general relativity to its most simple form, that cosmological constant there seems like an addition that we added on, and that now we accept as being there. So I'm wondering if in the same way in the future we might accept more additions to general relativity, even if it might somehow break the underlying aesthetics.
Yeah, but if you think about the cosmological constant, it ties in very well with the principles of general relativity. Whereas if you look at these additions to gravity that try to do away with dark matter or explain observations without dark matter, then you really add things only because you need to fit the observations and there's no underlying principle. But I wonder if I might pick up something from the chat actually, because this David Howden's comment that there are evolutionary psychology theories about why we find some things beautiful. So you already referred to this. Yeah, and I wonder how they would explain the concept of beauty in physics, because I'm not familiar with these theories, but let me go on just ignorantly. Commenting my point of view, which is that obviously the notion of beauty has evolved, is part of our evolutionary development. And I'm not familiar with these theories, so I don't know what they say in detail. But it's clear that if we consider, for example, that this notion of beauty, it really comes from structures that we observe, and mostly they're actually visual structures. Although there's also like auditory beauty. Though for some reason, for example, when it comes to tactile sensations, even though they could be pleasant, we don't use the word beauty, for tactile or olfactory sensations, which is somehow a bit funny. But if you just think about these visual sensations, then if you think, for example, about something like a circle, which has a certain aesthetic associated with it, and then it is this notion of simplicity and symmetry and beauty in a circle that underlies the geometric way that we look at beauty in physics. Because so we have a circle, and associated with the circle is circle is a shape such that the distance of all of the points from the center is the same. We can also phrase this another way, so that if we take a point and rotate it like this, we get a circle. So now we associate with the shape, we have an associated operation. And this is a mathematical operation of rotation. Now you can think about, rotating space and so on. And it's this, and you can have this abstract idea that is now disconnected, from the visual impression. And indeed, this notion of rotation is a very fundamental one, in many branches of physics. So I mentioned, laws of physics. So I mentioned Newton's laws of gravity, which are such that if you rotate them around any axis in space, they remain the same. But if you think about electromagnetism, the fundamental symmetry, the beauty principle, or whatever you want to call it, at the heart of quantum electrodynamics is invariance of the theory under a simple rotation on a circle. And when I at least visualize the beauty of quantum electrodynamics, then I'm using this idea of rotations. And then when you have more complicated theories of quantum field theory, you use these geometrical ideas, these spatial ideas that we are born with, that we have learned evolutionary. When we are born, we already have an idea of space. And when we grow up, of course, then this develops. But we have these evolved ideas related to concrete space, and then we use them to understand these abstract notions. So in some sense, there are these two different ways: algebraic way, so use the equations, and then this the geometric way, so that you sort of spatialize these ideas and try to be in the mental picture of them.
I think that's a really good point. And now on a complete tangent there, I'm wondering how people with aphantasia, how their concept of beauty is affected. So people with aphantasia can construct mental visualizations of things. I think that's an interesting direction that would take us way off topic. So I'm just leaving that as an open question if any neuroscientists want to jump on that. We have questions by Paul and David here that are very connected. And I think Paul's is a great one to lead us into a very interesting topic. So the question is string theory beautiful because it can explain so much, or is it ugly because it has so many more dimensions than other theories? And whether string theory is beautiful or not is something that is probably a contentious issue in the field.
So so first off, I've done some applied string theory or string-inspired cosmology, and my PhD was related to this sort of string-inspired models of cosmology with extra dimensions. But I'm not a string theorist, and I've never done sort of formal string theory. But my view, from when I studied string theory when I was a student and learned about the structure, is that indeed there is a lot of aesthetic value and beauty in the way you formulate string theory, and the way that you get these extra dimensions out is also actually quite beautiful. However, the version of string theory that is beautiful is the one that has these 10 dimensions, and has way more particles than we observe. Has a more complicated gravitational force than we observe. So it's one that doesn't really correspond to the real world. And I think the problem of beauty in string theory, that comes from the fact that then if you want to have something that looks like the real world, where where observers like us see only 3+1 dimensions, where gravity is like the one we observe, where the standard model is a good approximation for particle physics and so on. Then you have to do complicated, ugly things that are, again, basically only motivated by the observations. It's a bit actually like trying to explain observations without dark matter with modified gravity. You're just tuning things and adding stuff just to get the observations right. So there's no principle from which take string theory. There's no principle that will take you from the beautiful formulation of string theory in 10 dimensions to our world.
Yeah, I think that's really nice, because string theory is one that is often accused of being too beautiful, in the sense that we're so caught up on how beautiful string theory is that it's easy to ignore the fact that it doesn't actually describe the observations that we see.
Well, not the beautiful version anyway. I mean, you can have ugly versions that...
Yeah, if you take it in its most symmetric and simple and beautiful form, then it's hard to correlate that with the world that we live in. David Howden has a similar question. The many worlds interpretation of quantum mechanics, is it beautiful because it explains a lot, or is it ugly because it adds unnecessary or extra universes into the thing?
So I actually don't like this word interpretation that people talk about. So, the many worlds interpretation or this or that interpretation, because what is really at stake is taking the beautiful structure of quantum mechanics and asking how do observers like us see an approximately classical world where you don't see many of these quantum phenomena. How does this come out from quantum theory? And there, I don't think it's enough to say, so many worlds interpretation is basically just saying, the usual, the so-called Copenhagen interpretation is just that, whenever we observe, the quantum state collapses and then, and then continuous quantum evolution, and then we are by default classical observers. And this is very unsatisfactory because we are also built from quantum stuff. So you should start from describing your whole system as quantum and then explain how classicality emerges. And many worlds interpretation says that there is no collapse, there is nothing special, you just apply the rules of quantum mechanics and that's it. But what you should really do is explain how the world, again, the classical world as we see it emerges from quantum mechanics. We have gone some way towards that, for example, with decoherence. Very, some of this, but, some of the a bit related work on these quantum aspects was recognized with the Nobel Prize this year, but we are not still fully there. And so to me, it's many worlds interpretation about the beauty of it. I think it's a nice idea, but it's not really talking about the beauty of a, it's not a discrete thing. It's a proposal for saying, okay, there's nothing else to quantum mechanics, and quantum mechanics is of course beautiful. Or then you have other theories, like theories that explain you how the state of the system collapses, and then you can evaluate them. But it's a bit different because the many world interpretation is not a theory of physics. It's an idea about how this theory of physics might work.
There's a really nice comment here by Hemza that says it seems like our existence is only possible if we break some of this beauty or some of the symmetry, with the classic example of the baryon asymmetry or the matter-antimatter asymmetry in the universe. So then we could take that comment and ask the question of which I asked before and I want to come back to in a slightly different angle, does the universe require beauty or symmetry? And should we use beauty and symmetry as a guide when constructing our equations?
Yeah. So I don't think violation of the matter-antimatter asymmetry is a violation of beauty. I mean, if you look at, it's presumably, the result of a particle physics model that is beautiful. So if you think about my favorite model of baryogenesis, which uses these three light neutrinos, one of which is the dark matter, and then two of which play the main role in generating the baryon asymmetry. Then I think this model is quite beautiful. It also has a lot of symmetry. So again, I think that saying that beauty is lost because we no longer have as many baryons as antibaryons is again talking about, it's falling into the mistake, this pre-Newtonian mode of thinking about beauty, that you think about the realizations of the laws of physics and not the laws of physics themselves. So obviously the realizations of the laws of physics have less symmetry in them than the laws. As for whether the universe has to be beautiful, again, the universe is a realization of the laws of physics. So the question should be, if you talk about the laws, does the universe have to be governed by laws that are beautiful? So far, the idea of using aesthetics as a tool in physics has been very successful, and I would expect that it remains so.
I think one very nice example we can use here where the idea of symmetry and beauty actually led to a discovery is with Dirac's equations explaining particles, explaining the electron, because in order to be symmetrical and simple, he had to postulate the existence of negative energy states, which from a physics perspective didn't really make sense, but it really simplified the equations and it made Dirac's equations a lot easier to read and a lot nicer, more simple and symmetric. So he postulated this, even knowing that negative energy state is something we hadn't observed. And then a few years later, this actually led to the discovery of anti-electrons, which essentially have these negative energy states, at least in the mathematical description. So because of the idea of being caught up on, we need this equation to be beautiful, or this mathematical laws to be beautiful, it actually led to a physical discovery. So sometimes using beauty as a guide, as a good intuition, can be very, very useful. But then we can go to the provocative question that I put in the video description of, has this pursuit of beauty led physicists astray?
Yeah, I think the pursuit of beauty has not led physicists astray. What has happened is that we haven't had, okay, the problem is that the standard model of physics of particle physics has been so successful that we haven't found deviations from it in particle colliders, although we have been, searching since, now almost 50 years. And this means that we have not been able to observationally differentiate between different extensions of it. And these different extensions come with their own notions of aesthetics, their own notions of beauty, and also their own language, a bit their own sort of mathematical languages. And if you don't have observational data to tell you, okay, these versions are wrong, this may be right, then what happens is that then you put much emphasis on the notion of beauty that you're attached to. There's nothing to tell you that it's wrong. So I think it's true that people have become caught up with certain notions of beauty, like, for example, supersymmetry in particle physics, which I think is a beautiful symmetry to begin with, but its application to the standard model, I don't find particularly, to extensions of the standard model at low energy, one such that could be seen at colliders, I don't find particularly beautiful. But whether or not that's the case, it's indisputably true that we have not had any observational evidence in favor of it. And then if you just continue to neglect that you have no support for it, and just continue to evaluate everything from the notion of beauty, from the notions of aesthetics that are related to supersymmetric theories, then I think you can be led astray. But it's not the problem that you appreciate beauty too much. It's just you're just caught up in a certain ideal of beauty.
Yeah, I completely agree with that, and I think once we do, it goes back to what we were saying before, that if we find a new realization, a new observation that we need to, for example, expand on the standard model, we would then incorporate that into the accepted standards of beauty. Because at the end of the day, a theory needs to match the observations, and your theory can be as beautiful as you want, but if the observations don't match, then you're approaching it in the wrong way. So I think it is completely true that sometimes, because of the lack of observations in extensions to standard model, for an example, it's easy to say, okay, let's look for the most beautiful realizations, or let's look for something like this. But we do need to also be open to the possibility that those might not be the correct answers just because they are intrinsically symmetric. And also going back to the story you told at the beginning of how we discovered, leading up to Newtonian's description, the first idea that moving away from this circular orbit to an elliptical orbit seemed to be moving away from beauty. But as you said, we then discovered that this actually led to a much more beautiful description. So I think using beauty as a guide is important. It does give us good intuition, but it shouldn't be at the sake of actual observations. So observation should always supersede any sense of beauty.
Well, you know what Eddington said, you should never trust an observation until it's verified by theory.
That's also true.
So what I mean by that is that you also need a theoretical. So you also need a theoretical framework to tell you what to observe and how to interpret the observations, and of course also that what he was referring to is of course that some observations some of the observations will always be wrong.
Yeah, that is an important point to make as well, that sometimes observations can be wrong. And we have seen this sometimes at colliders where it looks like there's a hint of something that then disappears as soon
Yeah,
as
and
we
then
get
people
more
start
data.
chasing, oh, this would mean this and this and this. And, then people build, somehow elaborate stuff on this. But I think that's another aspect of the crisis in particle physics, that we haven't in colliders detected any deviations from the standard model. So if you do try to see something, then you try to latch onto it and see what could this mean.
Yeah, it is always interesting to see anytime an experiment announces new results. Within a week, there's about 700 papers trying to explain that result. And then when the result goes away, those papers are like, well, we tried. So it is always interesting to see. But of course, you do need your theories to be able to explain the observation. So if you get a new observation, it makes sense that people want to try to explain it. We have a very nice question from Paul here of how similar is our definition of beauty in physics to Occam's razor, which Occam's razor is the idea that if you have multiple ideas, sometimes the simplest one is more likely to be correct if there's no other thing to distinguish them.
Yeah. So Occam's razor is related to simplicity, and it's related, Newton also wrote about, against the notion of, like Occam, wrote about the notion of introducing things in the theory that are unnecessary. And indeed, if you look at Newtonian theory, it's really, as an all-encompassing explanation of what's going on, on Earth and the solar system. Then it's stripped of a lot of what we now view as unnecessary baggage. Theological baggage, astrological baggage, and so on, that earlier was associated, with the planets and with these sorts of theories. But I think so. But I don't think this notion of beauty in physics reduces to that, because Occam's razor is somehow a statement about simplicity, in the sense that your model should be as simple as possible, but no simpler than that. And the notion of beauty in physics is really more involved with that, because it's really, I think it's difficult to pinpoint it, because I think one way of phrasing this, in order to answer this question, about beauty in physics, I would have to really understand why physicists find things beautiful. But this is a difficult question. For example, I also don't know how to answer it. Why do humans find paintings beautiful? Why do humans find trees beautiful or something? Or why do we have these notions of beauty? So I only grasp parts of this problem related to this question.
Yeah, it's also very interesting because I think, I could have 10 people here and ask them what is beautiful in physics, and I would get 10 different answers. And I think there are some things we agree on, like general relativity is a very beautiful theory. But there are also things that we disagree on. So it is very hard to discuss this, because everything we say, as we said earlier, is coming back to our own conceptions and what we each individually find beautiful. But there does seem to be a trend that theories that have worked or that do provide accurate descriptions of the universe, physicists tend to think are beautiful. And someone made a comment quite a long time ago of, do we find things beautiful because we are intrinsically drawn to things that are correct in terms of physical laws? Or is there some underlying reason why we find these beautiful, going beyond whether they're correct descriptions of nature or not?
Yeah, so it goes back to the different languages and different standards of beauty. So there are, of course, theories, there are theories of physics that may be beautiful, but also completely wrong. So the fact that it's beautiful doesn't necessarily mean that it's the right one. But I actually disagree when you say that. I think you're maybe a bit too individualistic, because I think what we have is schools of aesthetics in physics. So that there are certain shared ideas within one school about what's beautiful. Certainly in particle physics, what sort of extensions of the standard model are beautiful and what are ugly. And I think people learn these ideas by socialization, not only by study. They learn these theories about beauty, or these ideas about beauty, not only by studying the theories and through their individual history, but also through socializing into the community.
Yeah, it's true. I know. I guess all of us, when we take general relativity in undergrad or whenever we take it, it's presented to us as this is the most beautiful theory. So that's the point we always start from of, okay,
Oh,
I'm
I didn't
about
know
to see
everyone
something
says this.
beautiful.
No, because I say that to my students, but I didn't know everybody else that does that too. Yeah.
I've had 3 different general relativity, or I've been to 3 different general relativity courses in different countries, and everyone introduced it as the most beautiful theory. So when you start with that, it's like, okay, I guess this is just a thing that physicists agree upon. I want a physicist someday to tell me, no, I don't think this is a beautiful theory, because I think that would be a very fun discussion.
Yeah.
On the topic of ideas that we think are beautiful that may or may not be correct, few people in the comments here are mentioning the idea of the big crunch. So this is the idea that when the universe, at some point the universe will stop expanding, it will collapse and go back in a cyclical way. So it expands and it collapses, it expands and collapses. And this has a very nice symmetry to it, and it's a very nice cyclical story, but it just doesn't fit the data. And people in the comments are arguing that, is the big crunch still a beautiful idea, even if it doesn't fit the data?
Yeah. Well, again, that's about the realizations of the laws of physics. So it's not about the laws of physics themselves. But also we don't know whether there will be a big crunch, because, we don't understand. We are not confident about the reasons for why the expansion of the universe has accelerated for the past 5 billion years. So I don't think we should be so cocky, and so arrogant as to presume to say what will continue to happen till infinity in the future.
Yeah, it's like based on what we observe now, this is what we think, but there's no reason why we couldn't have something that makes it stop, given that we don't know how dark energy works. If it even is dark energy that is causing the accelerated expansion.
Yeah.
Yeah, I think that's a great point. So we do only have 10 minutes or 8 minutes left of the stream now, so we've almost reached the 1 hour mark. So on the topic of beauty, is this, seeing as this was the topic you chose, is there something else you think we have to cover, or some other approach or angle, or something that we haven't yet said about beauty that you think we have to discuss?
Not really. Maybe there is actually one thing I'd like to say about related, because this evolutionary psychology thing was mentioned in the chat, and then I went on about that, how we observe, we have these visual impressions of some things, then we have mental abstractions of these that we use to grasp these abstract physical theories. But then actually it's these abstract physical theories whose realizations, whose phenomena are then these shapes that we observe. So I think it's kind of an interesting thing that you start with something concrete, you go into abstract, and then this abstraction explains these concrete thing, but in a completely different way than what you would have expected. And I think this also, and if we want to understand, if we want to answer this question, why do physicists find theories beautiful, then I do think we would have to go a little bit, into evolutionary psychology and how the brain works and how the brain finds certain patterns beautiful. And then it's also interesting because mathematicians talk a lot more than physicists about approaching theories or working algebraically or geometrically, with equations or then with these spatial shapes. And physicists, for some reason, in my experience, actually talk much less about that. And it seems to me that most physicists I work with somehow have less of these spatial models, these geometrical realization, using these, explicitly, consciously, applying these spatial ideas and these, that are connected to beauty, when they work with physics. And I'm not actually sure why that is, why that's the case.
I think this is something that should also be extended beyond just physics to other disciplines of science, because I'm sure if you take biologists or chemists, everyone will have different things that they find beautiful, both at the level of realization and at the underlying laws explaining that. I'm sure people working on the immune system must think it's an incredibly beautiful system, because it is ridiculously complex and amazing. And I remember early on in my streams, I would speak often to a neuroscientist. We've done a few streams together. And if you take a picture of the neurons in the brain, which looks a lot like the cosmic web, we both say that image looks beautiful for very different reasons. For me, because it's a representation of the structures of the universe, and for him, because it's a representation of the structures of our brain. So it does seem like even though the laws governing it are different, the ideals that we're attracted to are similar. So I think it would be very interesting to ask this question across different disciplines of what do you find beautiful in the science you do, in order to really get a broader perspective of what guides our sense of beauty in science.
Yeah, I think for me a more interesting question would be, how do you use beauty in your work? How do you use aesthetics? What sort of a tool is aesthetics for you? Because physicists, like particle physicists and cosmologists, talk a lot about beauty and ugliness.
That's true. Yeah, it's something that we do say a lot and does come up, but as you said, less than mathematicians. So it would be interesting to see how that plays a role in how different people develop different theories. So nearly at the end now, I'm going to ask you a question that you've probably already answered, but just in case there's a different answer to that, this is going to be a completely subjective question. In your opinion, what is the most beautiful law of physics or equation that we have? Are you sticking with general relativity, or is there something else?
Equation or law of physics? Yeah, I don't really actually think in terms of individual equations or laws, but rather like theories, structures to which they're connected. And then it would be, the understanding of gravity in terms of space-time geometry in the language of differential geometry.
So general relativity.
So general relativity, basically. But also, maybe my answer would be different if I understood quantum mechanics better, because in quantum mechanics also quantum mechanics understood in terms of linear algebra is somehow so simple. Linear algebra, and representation theory, and so it's somehow such a seemingly simple thing, and there's something very enchanting about taking this thing that is where you understand, like chess, that you understand. It's very easy to understand how the pieces play in quantum mechanics. What do? You have your your state space of vectors, and you have your linear operations, and you can add those vectors and so on. And then, but looking at from this simplicity, comes out this structure that is so counterintuitive. So there's something very enchanting about that. Oh, and of course, integration on the complex plane. Analysis on the complex plane has this really that's not physics, so that's mathematics, but that has this mysterious beauty about it.
Definitely. I think there are so many things that when I was thinking, like, how would I answer this question? But for me, it has to be Noether's theorem, which is the idea that every conservation law we see in the universe is linked to an underlying symmetry. I think this, while it's not necessarily one thing that you can tie to one specific phenomena, I think this is a really beautiful concept. Can be expressed very elegantly mathematically. And just this idea that if you have conservation of energy, conservation of angular momentum, all of these conservations you can relate to an underlying symmetry in a law. I think that's kind of applies to multiple laws, but I think it's just such a nice concept that it's the one I always come back to. If we're focusing purely on equations, theories, and mathematical descriptions, that's what I would bring out. Because I think Noether's theorem is just, the first time I learned about it, I fell in love with Noether's theorem, and I've never changed my opinion on it. But someone also mentioned in the comments earlier Maxwell's equations, which are also extremely elegant and extremely beautiful. We didn't discuss those at all. But I think there's so many examples that we could bring up of things that are beautiful in physics, both at the level of laws, but also going back to what you said earlier, at the level of realizations and at the level of the stories we tell about the laws and the realizations. So maybe just to wrap up on the question that I always ask everyone on the stream, apart from what we've discussed about today, what are you the most excited about in physics or in cosmology currently?
I'm usually excited about things that I barely understand. So meaning that are at the limit of that I have some idea of what's going on, but I don't really understand them. So for me, currently, it's really the quantum phenomena in inflation, quantum effects in inflation. So I'm doing a bit of work looking at the effect of these quantum kicks, so stochastic effects during inflation. So sort of looking at the all of according to our best understanding of the structure in the universe today is generated from quantum fluctuations during cosmic inflation in the first fraction of a second. And I'm doing work looking at in more detail what those quantum fluctuations are and what they do, but then also looking at this idea of, can we see some signature of the quantum nature of the origin of seeds of structure, like what we see in the cosmology background? Can we see it in the cosmology background, in the structure of dots? Can you see that they really come from a quantum process? And trying to understand this and also its relation to maybe to the quantum mechanical collapse problem. Or to put it more generally, the problem of why does the universe look classical? Because this is also something that when you think about it in cosmology, there is also this question of principle. How do we, why does the universe look classical to us? And then you can't appeal to saying, oh, we will observe it and collapse it because we are the product of this quantum mechanical process. So that for me is something that is maybe the most enchanting thing at the moment, and which I barely understand.
I think that's really cool, and I like the idea of being interested in things that you don't understand, because at its core, that's what physics is about, is finding a new thing we don't understand and poking it with a stick until we figured out what it is. And I don't think anyone has given that answer before, so that's a very nice answer. Maybe if you're up for it someday, I can get you back on the stream to talk about that as well, because I'm sure would be a very interesting topic to discuss here. Okay, so we have reached the 1 hour mark. So this has been really, really fun. Thank you for joining me today, Suksu. This is a topic we haven't discussed.
Thanks for the invitation.
Yeah, it was great to have you here. So to everyone in the comments, thank you so much for joining, for your questions, for keeping the conversation going. It's been really great to have you all here. Suksu, anything you want to wrap up on before I wrap up the stream? Anything else you want to throw out here?
Not really. It's been fun.
Awesome. Well, thank you so much for joining. To everyone watching and to anyone who catches the replay, Cup of Cosmology will be back next Sunday, same time as today. No specific topic in mind yet, but I'll figure that out during the week. So I hope to see you all again next Sunday, same time as today. And I hope in the meantime, you all stay safe and take care of each other.